didn't do too much, but we discussed about the elements of symmetry, and then
Okay.
we did optical isomerism in different types of molecules and all.
Mhm.
And then we studied enantiomers and diastereomers.
Okay, so you guys did conformations.
No, sir. Sir, what do you mean by conformation?
The projections, the way to draw a three-dimensional molecule in 2D.
Oh, no, we didn't do that yet.
How are you learning enantiomers? How is your sir teaching this?
Like, he's drawing the diagram, like the wedge thing.
Has he shown you what the diagram means? Has he discussed what the diagram means so far?
Yeah, he has.
So you know what each of those projections mean.
There are only two, right? So the dark one and the hashed one. Yeah. Or are there more?
Let me ask a question differently here. If I draw a molecule like this, which is what
Oh,
I'm guessing your teacher is doing now to an extent.
yes.
Do
Yeah.
you understand what that means?
Yeah.
Do you really?
It's,
What does it mean if I'm drawing a molecule like this? Explain what the vertical line means. What does the horizontal line mean? You saw the line, I suppose?
yeah, I saw.
Yeah, explain. So you have not learned that, but
No,
your
sir.
teacher is using this right now. You're
Yeah.
serious?
Yes.
That actually decreases my opinion of your teacher. I'm quite surprised that this is the same person who has been teaching till now. Okay. All right. You need to learn a concept called how to convert three-dimensional molecules into two-dimensional molecules. Let me start by explaining what this basically means here. In this here, you're going to be having this entire part is
Yeah.
going to be going away. These are coming towards you.
Okay.
You understand what I mean by that?
Yes, sir. Yeah.
No, you do not.
What?
You should not be able to at this stage. That's the unfortunate reality. So let's start off by taking a simple analysis as to, I mean, when you say you have understood, you understood what I said, but you didn't understand what I meant.
Yeah, I
So
guess.
let me try to start off with a simple carbon here. We need to learn about how to draw three-dimensional tetrahedrons or tetrahedral structure to 2D. This is a very important thing to understand, mainly because in different questions, they will give you in different stupid notations. If you do not understand how to interconvert between the notations, you are fucked then and there. You simply cannot touch it. How much ever you understand, you'll keep making mistakes in questions. You'll have to sit and memorize formulas here and there. You'll have to sit and memorize shit for this compound and that compound. You'll have to memorize scrap. If you do not understand how to interconvert between things, if you do not understand what each thing actually means. Now, let's start off with the first one, which you already know. Normally, when you want to convert a 3D structure into 2D, the 3D here basically means you're going to be having sp3 hybridization. There are 4 bonds. Okay, so when you're going to be having 4 bonds, the basic principle is when you have a planar, when you are drawing on a sheet or when you are representing it in 2D on a board or on a notebook or on a goddamn thing over here, whatever it is, basically you're converting it to 2D. In 2 dimensions, how many of the 4 can we place? There are 4 bonds now.
2.
Very correct. Why? Because we technically can only make a triangle. That's the maximum we can go about. So the moment it goes into one more dimension, it is out. So the idea here is you can only place 2 bonds on a plane. So when you're going to be having 2 bonds on a plane, These two bonds can mean anything like this. The remaining two fellows will automatically be the ones which are going to be the solid wedge and the hashed wedge. That is, when you place two bonds out of four, it doesn't matter which two, pick any two. You put two bonds on a plane out of the four, remaining two will automatically be something which you can place as a solid wedge, which means it's going to be towards the viewer, and a hashed wedge, which is away from the viewer. Now, when you're going to be having this type of solid wedge and hashed wedge applicable, that is going to be for a simple carbon. If I'm having one carbon or one tetrahedral unit, this is the way to proceed over here. Now, when you're going to be having multiple carbons connected, which is the next stage of the process here, you will have to start learning a slightly different way of projecting the same thing. So if you're looking at carbon-carbon bonds, the first projection which you need to look at and which you need to get familiar with is, I'm quite sure your teacher will teach you this at some point of time, dude. Do not assume your teacher will not. The way I see it, what I'm a little disappointed about is the order in which he's teaching shit. So it tells me he's not yet understood the little bit of the complexity here. So quite surprised, actually. The way he has covered your topics, he definitely has a lot of experience. He definitely has a lot of experience. Interesting. Okay, Okay, so first off is going to be what I call as the, I don't remember the exact name. It is, I think, called sawhorse projection. मुझे exactly याद नहीं है क्या नाम है इसका. Doesn't matter. Names are not my unnecessary game there to play with. So the point over here is, when you're going to be having multiple carbon-carbon bonds present together, you need to basically link them together. So let me start showing you the stupid thing there. So this is a simple. Okay. Give me a second. This is a simple tetrahedral system. Okay, as you can see, it's a nice clean tripod type. This central fellow is supposed to be the carbon. Okay, now in this particular case here, have a look here. If you're going to be looking at this plane, which is containing this bond over here and this bond over here.
Yeah.
Meaning there is a viewer on this side, let us say. For that viewer, this will be coming towards, this will be going
away.
From your point of view, what is going to be happening? You're going to be having nothing like this, like this. This is a more representative thing if I'm going to be taking it from your point of view on a 2D thing. So on this 2D plane here, if I'm looking at it over here like this, these two on the plane here. This guy is going away from you over here, whereas this guy is going to be coming towards you.
Yeah.
That's the idea here. So it doesn't matter which two bonds you take. Any two bonds you end up taking, you're always going to be having one bond going away and one bond coming towards you. That is the basic.
Yeah.
Now, that is a sawhorse projection. That is a solid wedge and hashed wedge projection. Sawhorse is basically going to be the same thing when you're going to be extending it for multiple carbons. So for instance, if I'm going to be having, say, another carbon added, another tetrahedral carbon added in. So let's make another tetrahedral carbon here. Just give me a second. So this is going to be yet another tetrahedral carbon here. So we're going to be having two of these now. All right. So when I have two of these, let me connect them up over here. So if I connect these guys up, now this is my system which we are studying right now. Correct?
Yeah.
This is going to be two carbons, CH3, single bond CH3. This is your ethane molecule.
Ethane. Yeah.
If I'm going to be having this ethane, as you can see here, it is a goddamn complicated molecule in 3D. And it can rotate also.
Yes, few rotations.
Yeah. It is going to be doing a lot of rotations. So when you're going to be having this kind of thing possible, my guess is your teacher will probably teach you all of this shit in conformations, where he'll teach optical ke baad conformation probably. That is not the ideal path, I would say. But anyway, coming back. So if you're going to be having, maybe your teacher is under pressure for exam syllabus. Is there an exam happening soon for you guys?
Yeah, but then we finished syllabus for that.
That is why he's probably rushed through. Okay. Is he setting the paper?
No.
Then I'm not sure why he's rushing through. Chalo, huh? Interesting. When is the exam?
Tomorrow, sir.
Aha. Aha. Optical isomerism is there or not there?
No, it's not there.
Okay. Till where is it? Is your syllabus?
Geometric.
Till geometric.
Yeah.
Do you want to discuss any doubts in that bunch, or shall we continue where we are?
It's fine, sir. Nothing as well.
You're confident properly? You practice questions till there?
Yeah, I've done a few. I've done my workbook. Yeah.
You've done your work for it.
Workbook, yeah.
You did that formula wala shit for the cistrons if you're having conjugated dienes. Multiple double bonded systems.
The number of geometrical isomers. Yeah.
You worked that out as well?
Yeah, we did that in class. Yeah.
And the formula approach you would have probably discussed in class.
Yes, and the non-formula also we did, like
Non-formula also.
where it does. Yeah, sir. When does it not work? Like, is there any like specific case where it doesn't work?
When you're going to be having what do you say, symmetrical systems, watch out for them carefully. The formula depends on how many levels of symmetry you have. For instance, I'm having, say, multiple double bonds, say 8 double bonds present in the system. There will be more levels of symmetry than we can imagine when you're going to be having, say, 2 double bonds present or 4 double bonds present in the system. 8 double bonds there, or let's say 16 double bonds. When you increase the n value there, then you will end up having much larger complexities at play. Especially when the n is going to be something which is going to be a 2 power n. So whenever you're going to be having a 2 power n type of, now when I say 2 power n, I mean, what to say, if the number of double bonds which are in conjugation is going to be some power of n.
Yeah.
Some power of 2, some power of 2. Some 2 power x something.
Yeah.
In that type of case, there will be a complexity which comes up with respect to the symmetry aspect there. That is the thing which I know doesn't work. Since I know it doesn't work there, I have abandoned that memorizing the formula completely. So,
can you give an example once?
Try 8 double bonds in conjugation. What happens when you're having 8 double bonds in conjugation? In the formula there, what are you doing when you're having symmetry elements?
2 power n.
No. Explain when you are having 4 double bonds in conjugation continuously. And there's a possibility of symmetry. Let's say there is going to be 1 carbon methyl group and 1 hydrogen. Then there is going to be 4 consecutive C double bond Cs attached.
Oh, consecutive is saying, okay.
Yes. Not consecutive exactly. Double bond, double bond, double bond, single bond, double bond, single bond, double bond,
okay,
single bond.
Yeah, that's what I thought. Okay.
So 4 of them. 3, 1 C double bond C, then a break, then there's another C double bond C, then a break. Usteka, I want 4 in one case. You have symmetry there, right?
You have symmetry about
in this case, it works nicely. So how do you do in this particular case? What's the formula you apply here? How do you apply the formula and do it here? Tell me.
You count the number of
there are 4 double bonds here. So 2 power 4 will not work
2
here.
power 4.
That will not work here.
Which is symmetric.
Yeah, there is symmetry here, no?
Yeah. Yeah. Right.
So how do you do it here? How do you apply the formula here?
So for symmetric, it's the n is even, right? So there's another formula for that. 2 power n minus 1.
Go with that, huh?
2 power n minus 1 plus 2 power n by 2 minus 1.
2 power n minus 1 plus
2 power n by 2 minus 1.
This will work for 4 now. Go with 8.
Same formula. 2 power 7.
The
2 power.
thing over there is it will not be n by 2 alone. It will be n by 4 also. You'll have to add in over here.
But why?
I do not know why. There is some symmetry aspect. That's what I'm trying to tell you here. When you're having two powers of x as the number of double bonds in sequence, now what happens is you'll have to basically add in your teacher's case, what have they given you? They've told you even number and they have bluntly mentioned it and moved on.
Yeah.
The problem will come not with even numbers. Even numbers ke liye ye kaam kar lega.
Odd numbers, maybe.
No, odd numbers ke liye you don't need that.
Odd numbers also there's a formula.
Even number of double bonds, this will work. The problem will come when it is not just even, but it is a power of 2 also. That is a very larger scale. Basically, I was bored a long time back. I sat and experimented on all of these formulas on MATLAB. So a bunch of these I stopped using. This was college time. So I was bored, a lot more bored than I used to be normally. So effectively, the problem here is this formula will work for most of your standard cases, like odds and evens at normal levels. 4 के लिए ये काम करेगा, 6 के लिए ये काम करेगा, 8 के लिए it will get tricky. If I have 8 double bonds continuously, what I noticed was one case which goes missing. One set of cases which doesn't get added up, mainly because it was thought to be symmetrical, but it is not symmetrical. Something of that sort.
When you say it is symmetrical, no? About the...
I do not know how to explain this to you at this stage, simply because this is something which is at a boundary level of my own understanding. It is not something I'm also not particularly clear about over here. So to an extent, I know it gets complicated for 2 power x. I do not know why it gets complicated. I know how to fix the complication, which is basically add one more thing over there. It will be n by 2 power जो भी power का आएगा
+1 2 power
उसका one level lower.
Yeah, by 2 again.
So n by 2 आएगा. In the next one, it will be n by 4. If you go even higher, it will be n by 8.
Okay, so if it's from between 8 and 16,
don't debate on unnecessary things. We have talked about these types of things before. There are enough things in the world which we basically can invest time on to understand a little bit better. There is enough gyan available in the goddamn world. There's no dearth of information. But that doesn't mean we have to invest our brain power, our mana capacity into unnecessary things just because they seem interesting. What is the purpose of that? The purpose is basically, it's like a YouTube video. YouTube video, what does it do? It basically traps you onto some bullshit. Yes, this sounds interesting. This is something which is interesting, but move on. So if you have understood the formula cleanly enough, apply it properly. No problems. But remember, when you end up having larger powers of 2, be careful. You have tested out for 2 power 2 tak, 2 power 3 may say, be a little bit more careful. That's all I would suggest. Same for optical activity also. A similar formula would have been probably provided to you in optical isomerism as well.
Yeah.
And similar logic applies over there as well. It also ends up having similar issues when it comes to higher powers of 2. Okay, now let's get back to what we were discussing. So sawhorse projection is basically going to be how you view this molecule on a 2D. So on 2D, if you have to view this molecule, the way to view it is, we put 2 bonds for each carbon on the same plane. All right, so per carbon, I can put 2 bonds on a plane. Correct. For each tetrahedral carbon, because it's sp3, you can't hear me clearly, is it?
No, I can hear you, sir.
So for each sp3 hybridized carbon, we effectively have 2 bonds on the same plane, which we can put over there. So I need to put 2 bonds on the same plane here. So which 2 bonds do we put on the same plane here? Make sure that the carbon-carbon bond between them is absolutely put on the same plane.
So that's the way to,
in this particular case here, the way to basically get it done is you put two bonds on the same plane. We are drawing ethane. I forgot about that, so I put carbons by mistake. So in ethane, we are going to be having this carbon. Let's call this as carbon 1. Let's call this as carbon 2. Carbon 1, we are putting one carbon hydrogen and a carbon carbon on the same plane. And for carbon 2, we are putting the carbon carbon and another carbon hydrogen on the same plane here. That's the basic principle. What's going to be happening then? Take this thingy again. What's going to be happening is, if I'm going to be having it like that, it's like this. Currently, let's have a look at the molecule like this. You can see the molecule. This is supposed to be the molecule over here.
Yes.
Let's say I'm going to be looking at making you look at the molecule from this angle right now, like this. What's happening here? You're going to be having this bond over here, and this bond over here, and this bond. All of them go onto the same plane of the camera plane, basically.
Yes.
This
Yeah.
plane.
Hmm.
All of them are present on this plane over here. So let's look at it from this angle now. All of them are present on this plane like this now.
Hmm.
And where my hand is present over here. This plane currently. Fair enough?
Yes.
Now, in this particular case over here, if you look at it like this, what's going to be happening here? You're going to be having each carbon becoming like a Y.
Yeah.
It looks like a Y to you?
Yes.
If I draw it like this, from the point of view of this plane, if this is the plane here, if a viewer is present on this side, these two bonds, this bond here, and this bond here, these two bonds that are on this side are towards the viewer. If the viewer is looking at it from this side.
Yeah.
That is, we are going to be looking at these two bonds here.
Yes.
Two bonds are coming towards you. Correct? So same way here, if I'm going to be having the viewer on this side, you're going to be having these two bonds being away from the viewer who is present on this direction over here. So if there's a viewer here, that viewer is going to be having these bonds coming towards him, and the viewer is also going to be having these bonds going away from that particular person. So the idea here is, when you're going to be having this bond being this particular structure being converted into 2D, you'll be having two things to be drawn here. This side will be a hashed wedge. This side will be a solid wedge. On both. Hydrogen here, hydrogen here, hydrogen here, and hydrogen here. This is basically going to be your structure for ethane here. Now, this is not the only way to draw it though. There are many different ways to draw it. This is why I think your teacher probably will teach this under conformations. When you're going to be having this molecule here, is this the only way in which the molecule can be? No, it can rotate. So let's say the molecule does rotate. If it rotates, if it is going to be present like this. In this case here, let's look at this plane now. This plane.
Yeah.
In this plane here, what's going to be happening is, we are actually going to be having these bonds on the same plane here. That is, we are actually going to be having this bond above here and this below fellow here, all on the same plane. That is the actual reality. You can't see it perfectly through this perfectly here. Let me put it in a more cleaner manner for you. Yes, this is the best.
There, yeah.
And you can see it like this now, correct?
Yes, sir. Yeah.
So you can see that all of the, this central bond here between the carbons, this top bond and this bottom bond, all of them go into the same plane.
Same plane. Yeah.
When they go into the same plane here, which is this plane over here, what's going to be happening? From a viewer on this side, these two bonds are going to be towards, and these two bonds are going to be away.
Away.
So what has happened is, we have had a rotation happening. What type of rotation? We had a rotation along the sigma bond. Originally, this was Y. This guy is still in the Y form. As you can see, this guy is still in your Y form. But what's happened to this bugger, this carbon here? This has become some kind of an inverted Y. It looks like a lambda, correct? So what did I do there? I had this initial Y changed because it got rotated into an inverted Y.
Yes.
And what type of rotation happened? Rotation across the central sigma. Carbon-carbon sigma bond, which allows free rotation. You understand the principle here?
Yes. Yeah.
So both of these represent the same structure. So let's say I'm maintaining carbon 1 a constant. Let's say I'm rotating carbon 2. So I'm fixing this bugger here. I'm going to be rotating this guy. So when I fix this fellow and I rotate the other one here, we're going to be having this hydrogen going up over here, and we'll be having
Inverted Y.
Something of this getting happening here. Inverted Y basically forming here. Now,
Yes.
this Sawhorse projection is something which you will be absolutely learning about soon enough in more detail. I'm quite sure your teacher will be teaching you conformations. There's no way he can escape from that. So that is something he'll definitely be teaching you. I'm just surprised he's not teaching that before your optical a little bit. So optical ke liye, it'll be nice to go touch that up, then go to optical, then come back to conformations. That is my preferred style when I'm teaching this. Till now, I have not seen your teacher deviate from my style so much. So, normally here I would go with conformations in the beginning a little bit, a touch up on it, then go into optical, then come back to conformations. I agree that conformations you have to go into in more detail after optical, but you need conformations to understand optical better. Now, let's come back to the next way which we can look at a molecule of this sort. The next way to look at a molecule is going to be called as Newman projection. Now, when I say Newman projection here, that is going to be not Newman actually. Newman projection, I'll not discuss this. This discuss in your class. Discussed in class later. Your teacher will definitely end up discussing this in class later. We'll discuss the third type. The third type is called as Fisher projection.
What is this?
This you know?
No, I don't know this.
So this is called as Fisher projection now. So the third type is going to be the one which you are seeing in optical isomerism fully. This type.
Okay, this thing, yeah.
So this kind of projection is basically referred to as Fisher projection. So what is this Fisher projection? The Fisher projection is like this. Let's take this molecule itself. Methane. Okay. I'm going to look at the molecule now like this. How does a molecule look to you? What does it look like?
There's a straight thing and then two extensions at both ends.
Effectively, what you are seeing now is you are basically seeing the straight
and two extensions at each end.
And the two extensions are going to be coming towards you, and two more extensions are coming towards you. Correct?
Yeah.
You do not see the back bond here.
Correct. Yeah.
You do not see this back bond over here. So effectively, what is happening over here is you're going to be having two bonds coming towards you on the first carbon and two bonds on the second carbon coming towards you. The central thingy you can see one bond for the first carbon and one bond for the second carbon cannot see because they are going away from you.
So what if it was rotated like this? And how do you draw it?
You can always rotate and play with it. But the Fisher projection, when you draw it like that, it means you are trying to bring the molecule in that thing and then seeing it. Rotate as needed. Every rotation is allowed. What do you mean by rotation is allowed? Every sigma bond can be rotated.
Yeah.
So let me explain a little bit more. When you have groups, you'll understand better when you have groups. Okay, so let's say we are taking two red fellows here. Okay, so in this case here, the red represents say some group. You're going to be having the hydrogens coming towards you, the methyl group. Let's say the red is methyl group that is going away from you in this particular case here. We can of course rotate it.
Yes.
This is going to be the same substance in another Fisher projection. That means that diagram, what was the previous diagram looking like? That previous diagram should have looked like this.
It looked like the ME were up.
Yes, so let me draw that first one. The first one should have seemed like this. We should have had a methyl here. We should have had a methyl here. We should have had a hydrogen here, hydrogen here, hydrogen here, hydrogen here. This was the first structure. Now this second one here is going to be something where you're going to be having hydrogen over here, methyl here, hydrogen here, hydrogen here, and you're going to be having, in this particular case here, a methyl here and a hydrogen here.
Yeah.
Right? On your right, there's going to be a methyl. On your left, there's going to be hydrogen on the top fill.
Correct. Yeah.
So this is basically that thing. This can still be rotated once more.
Okay. Yeah. Then left side.
Effectively, every possibility is allowed.
Yeah.
Bottom guy can also be rotated.
Yeah.
So bottom guy can also be rotated into something like this.
Yeah.
Every possibility is allowed. And how many ever possibilities you draw, all of them are the same. Why are they all the same? Because none of them are going to be representing a different molecule. They all represent the same final molecule.
Just viewed in a different way. Yeah.
Sorry?
Just viewed in a different way.
Yes, they are just viewed in a different way. After a little bit of rotation here and there. That's the idea so far here. Now, so when it comes to molecules, this is basically the Fisher projection over here. Now, when we are going to be looking at, what to say, optical activity, go on into what you have discussed so far.
Like, optically, so optically active means if you put this compound in, and if you project plane polarized light through it, then it'll shift. I mean, it'll rotate.
Yeah, okay. That we talked about already.
Yes.
Tell me something we have not discussed. We learned this week.